My speech today about linear map and derivative in non-commutative algebra. The speech of Professor Sirozzi on workshop Neutrons and quaternions and octonions in 2023 inspired me to prepare the speech. I dedicated my speech to linear map of non-commutative algebra as well the application of the theory of linear maps to the definition of the derivative. I also considered Newton's method to solve equation f at x equal a in quaternion algebra. We consider division of algebra A over ring D and found some statements are true for any D algebra. Let E be the basis of the algebra A, then E0 is the unit of the algebra A. Linear map of the algebra A is linear map of the module A. We use notation 2.1 for image of the linear map F. Let F be linear map of the algebra A. Then maps AF defined by quality 2.2 and FB defined by quality 2.3 are linear map as well. From this statement, it follows that for any linear map F of the algebra A and any tensor A stamp B, the map 2.4 defined by quality 2.5 is linear map as well. And tensor F from tensor square of algebra A has a representation 2.6 where A numbers f as 0, f as 1 are called companions of tensor. In the equality 2.6, I use convention as similar to Einstein's convention. If index is repeated in companions of tensor, then corresponding expression is sum for this index, and the set of values of the index is finite. However, this set depends on the tensor. According to this convention, the expression 2.6 is equivalent to the expression 2.7. This convention allows us to avoid excessive use of summation symbol in complex expression. For instance, you can compare left and right side of the equality 2.8. Because sum of linear maps is linear map, then the definition of linear map 2.5 can be extended to any tensor 2.6 using equality 2.9. If we introduce product 2.10 on the tensor square of algebra A, then tensor square of algebra A is the algebra, and the set of linear maps of algebra A is left module or tensor square of algebra A. In equality to the 10, I use different colors to see the order of the factors in the product. If module of linear maps of algebra A has dimension 1, then we can identify a linear map to 11 and tensor F from tensor square of algebra A. The representation 2.6 of tensor F is ambiguous. For instance, in equality to 12, you can see different representation of the same tensor. If we consider the basis E of the algebra A, then the representation 213 of the tensor F is uniquely defined and is called standard representation of the tensor F. The number Fij are called standard companions of tensor F. In the equality 213, I use Einstein's summation convention in which repeated index, one above and one below, implies summation with respect to a repeated index. Theorem. Let's see the structural constants of the algebra A. Let 214 be standard representation of the tensor F. and 215 be standard representation of the tensor G. The standard representation of product of tensor F and G to 16 satisfy equality to 17. This theorem follows another theorem. Let C be structural constant of the algebra A. Let 220 be standard representation of the tensor F. Let the exists tensor G, which is inverse power of tensor F, and 221 be standard representation of the tensor G. The standard components of the tensor G satisfy to the system of linear equation 222. If there does not exist tensor G, which is the inverse power of tensor F, then tensor F is called singular. Now we consider matrix operations. Now we consider matrices whose entries belong to associative division the algebra A. According to the custom, the product of matrices A and B is defined as product of rows of matrix A and columns of the matrix B. In non-commutative algebra, this product is not enough to solve some problems. We consider first example. We represent the basis E of right vector space V as row of matrix 3.1. We represent coordinate of vectors V with respect to the basis E as vector columns 3.2. Therefore, we can represent the vector V as product of matrices 3.3. Another example. We represent the basis E of left vector space V as row of matrix 3.4. And we represent coordinate of vector V with respect to the basis E as vector columns 3.5. However, we cannot represent the vector V as product of matrices 3.6 because this product is not defined. From these examples, it follows that we cannot confine ourselves to traditional product of matrices, and we need to define two product of matrices. To distinguish between these products, we introduce a new notation. Let the number of columns of the matrix A equal the number of rows of matrix B. Row-column product or RC product of matrices A and B is form 3.7 and can be expressed as product of row of matrix A or columns of matrix B. As we see, row-column product of matrices correspond to the traditional product of matrices. Definition 3.4. Let the number of rows matrix A equal the number of columns of the matrix B. Column row product or CR product of matrices A and B has form 3.10 and can be expressed as product of column of matrix A over row of matrix B. Now we consider linear equation for that one, where A is tensor. You can write down the equation for that one as equation for that two, or in more details as equation for that three. To solve the equation for that one, we choose the standard representation of tensor A and write down equation for that one as equation for that four. Period. Consider linear equation for that 5. If there exists tensor G, which is inverse power of tensor F, then the equation for that 5 has a unique solution for that 6. Now we consider example for the 2. Consider equation for the 7. in quaternion algebra. And that representation of tensor F that determines the left side of the equation for that 7 has the form for that A. So that representation of tensor G, which is left power of tensor F, has form for that 9. Therefore, solution of equation for that 7 has form for that 10. Now we consider solving of the system of linear equation for 11 and for 12 using Gauss's method. Coefficient of x1 in the equation for 11 has form for that 8. We consider this tensor in the previous example. Therefore, I multiply the equation for 11 over tensor for that 9. We found this tensor in previous example. And we get the equation for 15. To show the technique of calculation with tensor, I will consider product for 14 of tensor for that 9 and tensor for 15, which second coefficient in our system. In following calculation, I consider only final result. Since addition in the distributive with respect to multiplication, the equality for 16 falls from the equality for 14. I multiply each term in first sum over each term on the second sum. The equality for 17 follows from the equalities to that 10 and for 16. So I just apply equality to the 10 to each part of product in the equality for 16. For instance, equality for 18. Finally, the equality for 19 follows from the equality for 17. Because coefficient of x1 in the equation for 15 is identity map, we multiply the equation for 15 by coefficient for 20, which is coefficient of x1 in the second equation. And we get the equation for 21. Because coefficient of x1 in the equation for 21 and for 12 are the same, we subtract the equation for 21 from the equation for 12 and get the equation for 22, where coefficient of x2 is defined by equality for 23. From equalities for 22 and for 23, it follows that x2 is defined by equality for 24. And the equality for 25 follows from the equation for 15 and equality for 24. It remains to check that we find the solution of our system. Before we moving ahead, I consider the definition of norm the algebra. Norm on ring D is a map from the ring D to real numbers which satisfy following axioms. Norm is not negative. Norm of A equals 0 if and only if A equals 0. Norm of product equal product of norms, and norm of sum not greater than sum of norms. Ring Z and dot with the structure defined by given norm on D is called norm ring. Now, let D be norm ring with norm A. Norm of the model V is a map from model V into real numbers which satisfy following axioms. Norm of V is not negative. Norm of V equals 0 if and only if V equals 0. Norm of sum not greater than sum of norms. At norm of product V or scalar A equal product of norm of scalar A and norm of V. The model V and dot with the structure defined by given norm on V is called norm the model. Let D be a non-commutative ring. Let A be the algebra. The norm A on the model A such that product of norms not greater than product of norms is called norm on the algebra A. The algebra A and dot with the structure defined by a given norm on A is called norm the algebra. Next definition. Let A be norm the algebra. A number A is called limit of a sequence AN if for any real epsilon which is greater than 0, there exists positive integer and 0 depending on epsilon and such that norm of an minus a less than epsilon for every n greater than 0. We also say that sequence an converges to A. Next definition. Let A be norm the algebra. The sequence an is called fundamental or kosher sequence if for every real epsilon which is greater than 0, there exists positive integer as 0 depending on epsilon and such that norm a p minus a q less than epsilon for every p and q greater than 0. Norm the algebra A is called Banach the algebra if any fundamental sequence of elements of algebra A converges. Now we can consider derivative of map. Let A and B be Banach models with corresponding norm. The map F is called differentiable on the set U, which is a subset of A, if at every point X, the increment of the map F can be represented as inequality 6.1, where the F over the X is linear map of the model A into the model B, and O is such map that we have equality 6.2. Linear map the F over the X is called derivative of map F, and the differential the F of the map F is defined by equality 6.3, where the X is differential of the argument. Theorem. Definition of derivative 6.1 is equivalent to the definition 6.4. Based on this theorem, we can consider some examples of derivative. Derivative of identity map is identity map. Derivative of linear map is linear map itself. Let D be complete commutative ring characteristic 0, and A be associative Banach the algebra. Then derivative of x squared defined by equality 6.7. It's very easy to prove this theorem. We consider increment of the mach x square inequality 6.10. We first open this term by full square and get this equality. Equality 6.7 follows from this equality. Similarly, the derivative of x cubed is defined by equality 6.11. One of the applications considered above theory is Newton's method to solve the equation 7.1, where f is a differentiable map. Newton's method is an iterative method for finding the root. On each step of iteration, we have initial approximation x0. We assume that the curve in the neighborhood of the point 7.2 can be approximated by tangent. The point 7.3 of intersection of tangent and axis x is the initial approximation for the next step of iteration. Iteration is finished when the value f of x0 gets small enough. We consider Newton's method in non-commutative norm algebra. According to definition 6.1, you have equality 7.4 in the neighborhood of the point x equal x0. If we require f of x equals 0, then equality 7.5 follows from the equality 7.4. If there exists an objet which is inverse part of the derivative, then the solution of linear equation 7.5 is initial approximation for the next step of iteration. Now we consider the map 7.7. In quaternion algebra. The derivative of map F is defined by equality 7.8. To solve this equation, I use application which I wrote on C#. First initial value will be 1 plus I. First iteration. Here we see the value of function on this value. Next step. We see that function becomes smaller and smaller. Next step. We see that our iteration converges to value x equal I. Now we consider another approximation. For first initial value, I get value 1 plus j. And we start iteration. Now we see that our approximation converges to value j. In the field of functions of real variables, Newton's method may diverge. For instance, it may happen when first derivative is positive and second derivative change sign from positive to negative. Study of such criteria in the theory of function of complex or quaternionic variables give us additional knowledge about the behavior of corresponding maps. We consider value 1 plus k. And we see that our iteration diverges.